Hi, and welcome to the second video, picking up where we left off, dealing with fractions, but now the payoff is showing how this helps us get more problems right in chemistry, how it helps us think about units, and just improves our performance in general. So going back to what we were doing before, here's another math-looking problem, 12 times 3 over 18 times 7 times 18. And if I asked you to solve this, again, I'll grant we could take out a calculator and get a numeric answer to this. That's not the point of these exercises. The point is to show how we can manipulate symbols just like we manipulate numbers. So in this particular case, I'm going to do something that I think we know how to do, which is just show that we could cancel those two numbers, and then we would end up with 12. I'm going to write it for particular purposes that I have in mind. I'm just going to switch the order in which I write these things. Sorry, the camera doesn't seem to be focusing. There we go. I'm going to write it as 12 times 7 times 3, because we know that when we have multiplication, it doesn't matter the order in which we write things. So we would at least see that the 18s cancel. Now, I'm going to go down to something that maybe looks a little bit more familiar. There are 12 inches to a foot. So if we had a piece of wood that was 7 feet long, let's say, and we wanted to convert that into inches, we could do exactly the same thing as we just did with the symbols. Notice the 18 is taking the place, the feet is taking the place of the 18. So whereas we canceled the 18s, here we're just going to cancel the feet. And then we would be left with 12 times 7. Those are the numbers. We collect the numbers together. And then we had a 3 that was still hanging there. Well, in this case, we don't have a 3. It's just inches. Okay. So again, we're just treating everything the same. We don't write a little multiplication sign there. But if that had been a number, we could just imagine what we would do with the number. And in fact, now we could take 12 times 7, 14, 7, 8, and we could say that that's 84 inches. So in this case, then, we know that we have the units that were specified if we wanted to know the length of the board in inches, but we're given it in feet instead. So here's a similar problem. You might even guess where this is going. But if we took 12 times 3 times 18 times 7 times 18 times 2.54 times 6 divided by 3, I'll give you a second to write this down if you're taking notes. So we're going to cancel the things that look identical to one another. The 18 and the 18 look identical. The 3 and the 3 in this case look identical. And we would be left with 12 times 7 times 2.54 times 6. So that's a decimal. These are multiplications, so I'll put a little bracket around those. And then in the denominator, I didn't point this out before, but since we canceled the feet in the denominator is really just 1. So we have 84 inches over 1, or 84 inches. Here, both the 18 and the 3 cancel. So in this case, the denominator completely clears, becomes 1. And we could then take 12 times 7 times 2.54 times 6, and we'd get an answer. And that would be the answer, because anything divided by 1 is itself, which is exactly where we started in the very first video. Well, here's the analogy to that previous problem. 12 inches per foot times 7 feet times 2.54 centimeters per inch. So imagine we had that 7-foot board, but we didn't want to know how many inches it was, but we wanted to know how many centimeters it was. So just like we did before, the things that look identical, we're going to cancel. So feet cancel feet, inches cancel inches, and then we collect the numbers that remain. So we'd have 12 times 7 times 2.54 in the numerator. We also have centimeters remaining in the numerator. All of the denominator has cleared. I should also point out that all of these would be like one, the one in the denominator is implied when we just write the number. So the whole denominator becomes 1. So we could then take a calculator and do 12 times 7 times 2.54, and that would be the answer in centimeters. In fact, if I do that, we get 84 times 2.54, we get 213.3. So 213, I guess rounding up 0.4 centimeters. Without that unit, the answer would be wrong, because if I just walked up to you and I said, hey, that board is 213, what a long, short piece of wood, we don't know. So the units have to be specified if we're going to communicate in chemistry or really in any discipline. So the unit is just as important as the number. And in fact, when I teach, I think the unit is more important, because I really don't care how long this board is, 7-foot board. I'm not asking you about a 7-foot board. I'm asking you about the units and whether or not you know the conversions. So on exams, that's what would be being tested. And most textbook authors really don't care how many moles are in 27 grams of boron. They're really testing you whether or not you know how to do the conversions, and the units will tell you if you know how to do the conversions. So so this is, we don't often deal with dimensions of feet, centimeters, and inches in chemistry, but it does introduce units. But here is a chemical problem. Some of you may know this equation, PV equals nRT. This is the universal gas law. If you haven't seen the universal gas law, don't worry about it. You're going to be able to use it in about 3 or 4 minutes. And you're going to be able to use it confidently, because we're going to know that we get the units right when we do use it. So this is an equation that's useful for predicting pressures, P, volumes of gases, V. So P here is pressure. Volume is represented by V. T is the temperature. R is a thing called the universal gas constant, meaning it's just a number, but a number and a set of units that we need to know. And T is the temperature that the gas is at. So really what this says is, if we have a box full of gas, and if we know the volume of the box and we know the temperature that the gas is at, I haven't specified what N is. N is the number of moles. Many of you might be familiar with the idea of moles in chemistry. A mole is just a collection of molecules. If we have 6.022 times 10 to the 23rd molecules or atoms or paper clips or pens or trucks, that is a mole of those things. A mole is not specific to chemistry, just like a dozen isn't specific to, say, donuts. If you have 12 cans of Diet Coke, you have a dozen Diet Coke cans. So a mole just represents a number, 6.022 times 10 to the 23rd, just like dozen represents 12. So N just really represents how much gas do we have. So if we know how many moles of gas, and we know the volume, and we know the temperature, and we know this constant R, we will be able to predict or calculate the pressure, which could be useful because we want to know if the pressure is going to blow the sides off of the volume of the container that we have the gas in. I want to focus on the units, though, not so much interested in the actual numbers. Pressure, one of the common units of pressure is atmospheres. So you might hear about atmospheric pressure. So we use atmospheres to measure pressure. V is the volume, and that's often given in liters. So L is the abbreviation for liters. N is just written in terms of moles, so we often just use the abbreviation MOL. R is a collection of units, and here we have liters times atmospheres divided by moles time Kelvin, and temperature is in Kelvin. So here we see that we've got a ratio of units. So all of the material, all of the things we talked about in terms of ratios and how to deal with symbols in ratios in the last video come back in this video in solving chemical problems like this one. So let's suppose that we wanted to do a calculation and somebody said we've got a pressure of 2 atmospheres. So they've measured the pressure of this gas. They know that they've pumped in 6 moles of gas into that box. R, the universal gas constant, is 0.08206 liter atmospheres moles Kelvin. So this is liters times atmospheres divided by moles times Kelvin. And Kelvin, temperature rather, let's say temperature is 300 Kelvin. If you're not familiar with the Kelvin scale, don't worry about it. It's just a different temperature scale. We're used to the Fahrenheit scale, but we often use Kelvin in chemistry because it's a more absolute scale. So because we know pressure and we know moles and we know R and we know T, the only variable we don't know is the volume. So we could solve for the volume. This would tell us how big a volume this particular gas would fill. So how big of a balloon, let's say if we were blowing up a balloon, how big would that balloon get? Well, if we plug these things in, we get PV equals nRT. We would plug in what we know. We'd have 2 atmospheres. We don't know volume. We have 6 moles. R is 0.08206 liter atmospheres times moles times Kelvin, divided by moles times Kelvin, times 300 Kelvin. Notice that I am including the units and the numbers. I would encourage you, if you are not already in the habit of doing that, as soon as you start taking chemistry and biology and math, if there's anything that has units, include the units and work with them as you are working with the numbers, because it'll help you not guess at the units at the end. And we'll see how valuable units can be in just a moment. Okay. So if we want to solve for volume, lots of ways to do this. I'll admit that in terms of cancellations, but I will just go ahead and isolate volume on the other side. To do that, I'm going to multiply both sides by 2 atmospheres. So then the volume turns out to be 6 moles times 0.08206 liter atmospheres mole Kelvin times 300 Kelvin over 2 atmospheres. Now, just like we did above, we're going to collect all of the numbers together and collect all the units together. And we'll do that because it makes it easier to see the cancellations of the units and then convince ourselves of what the actual unit is that we end up with if we do the multiplication that we said we're going to do. So here we would have 6 times 0.08206 times 300 over 2. And then unit-wise, we have moles times liter atmospheres over moles Kelvin times Kelvin over atmospheres. So you see here we have a complex fraction. Well, that shouldn't scare us because we dealt with complex fractions before. We know how to deal with complex fractions, which is we're going to look at the numerator first, then we're going to look at the denominator second. Well, the denominator is easy. And then use what we know about manipulating symbols to come up with what the remaining unit would be. So if we look just at the numerator and treat it alone, we essentially have, I'm going to write it below, we have moles over 1 times liter atmospheres over moles times Kelvin over 1. That's the numerator. And we still have atmospheres in the denominator. Well, we know that the cancellations, if this were 3 over 1 and something over 3, those are canceled. So moles cancel moles. And then we have Kelvin canceling the Kelvin. So we have Kelvin in the numerator, Kelvin in the denominator, all in the numerator of our complex fraction. So it looks like then our numerator becomes liter atmospheres over 1 times 1 times 1 times 1, or liter atmospheres over 1 over atmospheres, which is really just liters times atmospheres over atmospheres, which again would be like our example 7 times 3 over 3. The 3's cancel, things that are identical cancel, and we'd be left with an answer of liters. So we know by looking at this and manipulating the symbols, the units, that all of this condenses to liters and that our answer is going to have the units of liters. And at this point, we ask ourselves, does that make sense? Before we even do the calculation, does that make sense? Well, yeah, because we're solving for a volume. So our volume should be some kind of three-dimensional shape. And a liter, if you think about a liter of milk or a gallon of milk, that's a three-dimensional volume that is being carved out by that unit. If we were solving for pressure, we should end up with something like atmospheres or torrs. If we were solving for temperature, our units, if we've arranged things correctly, our units should be Kelvin. If we don't get the right units, and this is the important thing, if the units don't turn out to be right, then this is going to be wrong. Doesn't matter what number we calculate, we've done something wrong with the way we've manipulated the whole equation. So the units are a quick check on, am I going to get this problem right? So now, knowing that my units make sense, that I'm going to get liters, I know I'm calculating a volume, so then I just have to correctly use my calculator, take 6 times 0.008206 times 300 divided by 2, and maybe I've done this incorrectly because I'm hurrying. I get 73.8, but more important than the 73.8 would be liters, because if I just walk up to you and say, I just drank 73.8, without a unit, it doesn't mean anything. So we have to specify the units. 73.8 thimblefuls is a very different story than 73.8 liters. This is an enormous volume. If we think about 4 liters to a gallon, if you were to divide this by 4, you get about 18 or so gallons. So if somebody walks up to you and says, I just drank 73.8 liters of water, I mean, they couldn't possibly do that. That's 20 gallons of water, or well, 18 or so. So the units are just as critical to communicate as the number is. But the units tell us that we're at least dealing with the volume, and as long as I've done the multiplication correctly, things would work out. So hopefully that convinces you a little bit of the utility of following the units, because it does help you get things right in terms of answering questions. But here's another example that I think is even more important, which is that it can help us, it can save us from having to memorize a lot of stuff. Right? And a lot of people don't like memorizing things. So let's take the example of the relationships between distance, time, and velocity. So we know that when we're talking about distances, like if we're talking about a car trip or something, we typically deal with miles. In the US, that would be the case. In other countries, we might be talking about kilometers or something, but distances are often in miles. Time here, for car trips, we're usually talking about hours. And velocity then, or speed, would be miles per hour. How many miles per hour are you going? And you're probably already thinking, hey, I know that there's an equation that relates these three. And maybe you know it. And if you know it, great. And you'll never forget it, terrific. But for me, I don't tend to memorize these things. And when I do, they don't stick with me unless I've used them. So I know that there's some relationship, but what is it? So if I really did want to solve for a problem, if I wanted to know how long it's going to take me to get somewhere, what do I want to multiply or divide by what? So I could think, well, maybe it's time is equal to velocity over distance. So maybe that's my hunch. I don't remember. Let's try that. Well, if we do that, we think about the units that we've talked about. Time is in hours. And then what we're really asking about is, does that equal this ratio? Well, velocity was miles per hour, and distance is in miles. So let's look at the right side of this equation. Sorry, the camera keeps wanting to focus. So we have miles over hour divided by miles, one of our complex fractions again. Well, how do we clear this? Well, we know we want to get the denominator equal to 1, so we're going to multiply by 1 over miles in the denominator. Multiply up here then by 1 over miles as well, so that we're really multiplying by a ratio that's equal to 1. Denominator cancels, so the denominator becomes 1. Miles in the numerator of the numerator cancels miles in the denominator of the numerator, and this becomes 1 over hours. And 1 over hours over 1, anything over itself is 1. So 1 over hours over 1 is equal to 1 over hours. Is that equal to hours? Now, I've had students say, well, close enough, right? Because hours show up and everything else cancels. So yeah, I must be right. So this must be the equation. And that's not right. This is where the units actually tell us, if we pay real close attention and strict attention, that we've done something wrong. This is akin to saying 3 is equal to 1 over 3. Or 100 is equal to 1 over 100. Now, we can pretty quickly recognize that those things don't make sense, that those aren't equal. So I shouldn't be writing these things. These are not equal. But that's what we would be saying if we said this, or if we were content to say, oh, close enough with the units, I'm in the ballpark, there's hours showing up. If somebody offered you $100, or they offered you 1 over $100, which would you rather have? $100, right? 1 over 100 is a very small amount of money. So if we're unwilling to accept that as an equality, we should be equally unwilling to accept hours is equal to 1 over hours. It's intellectually tempting to do that just because we don't like units, but it's really screaming at us that something's not right. So we have to try again. So this is not the right relationship. Okay. Well, I still don't know it, so let's try some other things. Distance times velocity, maybe that equals time. Is that right? I would encourage you to pause the video at this point and look at what happens to the units here. Okay, so if we think that that might be the right equation, we would get miles is distance, velocity is miles per hour. So just going back to our definitions up here, does that equal hours? Well, in this case now we get miles times miles, which would be like 3 times 3. Well, we express 3 times 3 as 3 squared. So miles times miles would be miles squared, and we still have hour in the denominator. Does that equal hours? No. So our units are telling us that we don't have the right equation. So even before we start plopping numbers into the equation that we're guessing at, we know that this isn't the right guess. Right? So it's saving us from getting something wrong. The units are helping us. They're guiding us. So this isn't right. What about maybe it's time times distance is equal to velocity? Well, time is in hours, distance is in miles, and does that equal miles per hour? And again, we'd have to say no, because rigorously, this is hours times miles. That's not equal to miles over hours. There's a difference there. And we, again, just can't wave our hands and say, oh, well, close enough. Because we wouldn't say 3 times 4 is equal to 3/4, right? We know that's wrong. So this should be equally incorrect to us. So that can't be right either. Finally, we could try something like distance is equal to velocity times time. So we're just playing around. Distance is miles, velocity is miles per hour times the time. We said time is in hours. Now when we look at that, we're asking, is that the right equation? Hours cancel hours, and we get then miles is equal to miles. So now we know that this is the right equation. So even if we didn't remember it and just knew that there was some relationship between those, we can use the units to tell us what the correct relationship is, which is really cool because then it relieves us from having to memorize that stuff. And it also helps us in cases where we don't remember. We don't have to throw up our hands and say, oh, I can't possibly solve this, I don't know, because we can figure it out. So now if we wanted to solve for how long is it going to take me to get there, and we know that we have a 340-mile journey and we're going to be traveling at 65 miles per hour, how long is it going to take? And now we could solve for t. We'd take 340 miles, divide by 65 miles to an hour. That's going to equal the time. We do exactly what we've been doing with ratios. We have 340 miles. If we multiply by hours over 65 miles in the top and the bottom, we'd have 340 miles times hours over 65 miles. All of that would be over 1. Miles would cancel miles. We see that we're going to be left with an answer in terms of hours, which is good because we wanted to know how much time it's going to take. So 340 divided by 65, it's going to take us 5.23 hours to make that journey. Which, being from Chicago, that distance wasn't arbitrary. That's about the time it takes me to get from Des Moines to Chicago, about 5.5 hours. So I've done that calculation before. But again, the point is that we were able to arrive at the right relationship simply by analyzing the units, and that's very powerful. So I hope that helps convince you to, when you're working initially in Gen Chem, get in the habit of using units, get in the habit of being comfortable canceling them, because canceling them is just like canceling numbers. If you ever get confused by units, put numbers in place of them and say, what would I do if this was a 7? Or what would I do if this were a 3? You might be perceiving that 3 and 7 are my go-to numbers for this. And that helps. It demystifies it. And again, we get more points on problems, on exams if we follow units and things like that. I hope you found this useful. I will be posting videos on other topics as well that are hopefully useful to you too as you begin general chemistry, biology, and math in a few weeks. Thanks, and have a good day.